Hey guys, Mr. Betts here. I want to continue talking about different ways that we can determine whether a series converges or diverges. And so we're going to extend the ideas that we learned with the integral test, and we're going to apply that to a specific type of series. So, first of all, the harmonic series, which is the first series that I have listed here, is one that we should be familiar with already. That is a series that is essentially 1 plus 1/2 plus 1/3 plus 1/4. So the denominator is just increasing by 1 each time. I do want to point out the harmonic series could really start at any one of these terms and go from there. So starting at 1/3 and going from there would still be the harmonic series. That is a series that in a couple of different ways we have shown diverges. So the integral test was one of the ways that we showed that. So if you remember the integral test, we can rewrite essentially or look at an associated function and look at the integral from 1 to infinity of 1 over x with respect to x. And if that integral converges, then the series is going to converge. If that integral diverges, then the series is going to diverge. Well, this is something that I went through in the last topic, so I'm not going to do that again with these specific examples. But if you remember, the harmonic series diverges. This series 1 over n squared converges. This one diverges. This one diverged. This one converges. And then this one diverged. And so all of these series, including this one, but we're going to exclude this one, all of them fit into a specific pattern, which is a series that is essentially the sum of 1 over n to some power. And it is an infinite sum. And so, what I want to look at a little bit more generally is how do we determine, without having to use the integral test every time, whether a series in that form will converge or diverge. So, let's use the integral test and do that with a general power on this. So, as long as p is a positive number, if p were negative, if p is less than 0, this is the same thing as essentially n to some power that's positive, and these terms would not be approaching 0. So as long as p is greater than 0, the denominator is getting bigger, which means the terms are approaching 0, and the nth term test for divergence says, well, it could converge or it could diverge. Also, since p is a positive number and the denominator is increasing, then that means the terms are decreasing and the integral test will apply. So the associated function then is going to be f of x equals 1 over x to some power. So let's look at the integral from 1 to infinity of 1 over x to some power with respect to x. And I'm going to do this assuming that p is not equal to 1. I will look at that case specifically, and in fact, we've already looked at that case. If p is 1, we've got the harmonic series, which we know diverges. So I'm going to look at this for all powers where p is not equal to 1. And the reason I'm going to do that is because where p equals 1, we cannot use the power rule for taking the antiderivative. When p equals 1, when p is not equal to 1, we can use the power rule. So let's first rewrite the limit. So c approaches infinity, 1 to c of, I'm going to write this as x to the negative p with respect to x. So as long as p is not equal to 1, that antiderivative is going to be x to the negative p plus 1 divided by 1 minus p, and we're evaluating that from 1 to c. So that will be the limit as c approaches infinity. Actually, let me go underneath here. I'm going to need a little more space. Of x to the negative c plus 1 over 1 minus, c to the negative p plus 1 over 1 minus p, minus, plug 1 in there, we're going to get 1 over 1 minus p. So if you think about what's happening here, if this exponent here is some positive number, then this whole term here is going to approach infinity because c is approaching infinity. So if we have a really big number in there for c, and a big number to a positive power is going to be a really big number. However, if that exponent is negative, what that's going to do is it's going to make it 1 over a really big number, and this is going to approach 0, and this is going to be finite. So this will converge if 1 minus p is negative, which means that p is greater than 1. On the other hand, it will diverge if that is positive, meaning that p is less than 1. So looking at this right here, if we have a series that's in that form, 1 over n to some power, if that power is a number bigger than 1, the series will converge. If that power is a number less than 1, the series will diverge. Also, if that power is 1, then we have the harmonic series, and it will also diverge. So this gives us what's called the p-series test, that says the sum of a series, the sum of an infinite series. Notice that there's no starting value here for n, because we could have some finite number of terms added on at the beginning or dropped off at the beginning. But some infinite sum where we have 1 over n to some power, if p is greater than 1, that series is going to converge. If p is less than or equal to 1, that series is going to diverge. P cannot be 0. If p is equal to 0, or if p is less than 0, then the series is going to diverge by the nth term test for divergence. So it's only really relevant if p is some positive number. The integral test would not apply if p is 0 or if p is negative, but the nth term test in that case would tell us that the series would diverge. So one way to think about this is that the harmonic series is going to be kind of the edge, the border here. And by making p a bigger number, we're going to make the denominator bigger, which makes the term smaller and makes it more likely that the series would converge. So the bigger the denominator is, the more likely it would be to converge. The smaller the denominator is, so by making p smaller than 1, then the terms themselves are going to be bigger, and the series would be bigger than the harmonic series, which we know diverges, and so that series would diverge.